Hello, I am David Métivier. I am postdoc at the Los Alamos National Laboratory at the Center for Nonlinear Studies. In the two lecture I propose, I will introduce you, if you've never seen it, dynamical systems and how we can study them using spectral analysis. Also, what will be new comparing the other talk is that I will allow the dimension of the problem we study to go to infinity, which, as you will see, will bring some change in the spectrum. So yeah, just to give you a quick mental picture of what it could be, this infinite dimensional system is, imagine a matrix with an infinite number of rows and columns, and you have to get the spectrum of that matrix. Um, so I don't know all of your background, but so if I forget to introduce some concept or some stuff are not clear for you, you can contact me through this email or ask Francesco. I don't know. Um, yeah. So there will be there is four parts, and I will in first lecture do the first two, and the last two in the second lecture. So what is this lecture? It's basically very small and quick introduction of dynamical systems. I won't introduce everything. I will also, as I say, introduce the concept of infinite dimensional systems, try to compare them. I will put a lot of some examples that sometimes you might think it's just a detour. Why are we doing that? But I hope it kind of makes sense. And also I believe that with example concept or new concepts are more clear. The main application I will look at will be the mixing phenomena and the synchronization phenomena. Synchronization, for example, imagine a cricket singing at unison. It's is a synchronization phenomena. Yeah. So what this talk is not, it's not, as I say, like full introduction. I will not introduce many uh, common term in those fields. I just want to give you a quick picture, and it's not a math lecture also, so I won't be putting many rigorous definition or proof. So what are dynamical systems? So they were like introduced by Henri Poincaré. He was French mathematician. He did many things, and amongst that, he popularized this formalism. So here you recognize a differential equation. I will use this notation x dot a lot, and you see x dot here is equal to some function k of x. Okay, so that can be linear or non-linear. So in the case where it's linear, in general, we know how to solve that. Maybe not if x is a vector with a large number of components, but if it's non-linear, in general, we don't know how to solve it. So in fact, keep in mind that most of differential equation, we don't know how to solve them exactly. So the idea of Poincaré, I guess, was that if we don't know exactly how to solve that, we'll try to study this equation with a different manner. So we'll use a kind of geometrical point of view. So for example, here, if this function here is positive, k of x is positive, it means that x will increase because the variation of x will be positive. So x will increase, and vice versa. If it's negative, it will decrease. If it's zero, it means that x will stop evolving, and you reach some steady state. Okay. So basically, this description, as you will see, has a very some kind of universality. And the question will ask are like, what can be the trajectory for a given k of x in time? How my system will evolve? Is there any steady state fixed point? So when k of x is 0, are this steady state stable or not? Imagine your system reach a steady state. If you perturb it, will it remain the same? And to answer that, we'll use the spectral analysis. Does my system has some oscillation? I briefly mention that it can happen chaos. It's a technical term, not chaos. Yeah. So now, what dynamical system? I kind of already said that, but what are they for? So the idea is that they can, with a simple formulation, each term of the differential equation will now have a simple interpretation. So that is why they are used widely, in fact. So dynamical systems are largely part of complex systems because basically in every field as is a dynamical system. If you want to model, let's say, a phenomena like how the employment rate varies in time, you will try to formulate some kind of model, a reduced model, some kind of dynamical system that has some oscillation. And with the simplest ingredient in this model, if you are able to provide oscillation, it means that you kind of understood what was the effect of each terms in the affecting the employment rate. And so you can say my model is kind of a valid model. Of course, then you can add many subtleties, many additional terms to your model, but you start always with simple, very simple model, and I'll show some. So yeah, basically, as I say, it's not just economy, it's every field. Biology, chemistry, physics, every field use dynamical system at some point. Now, the question I will ask again are how dynamics is influenced by the spectrum and what's happened if I go to infinite dimension. So let's start with the simplest example one can think of for a dynamical system, or one of the simplest. It's not the simplest actually. So this double dot means double derivative. So I hope you all seen this equation. It's equation that can modelize how this pendulum will oscillate in time. So x will oscillate like that. And basically this is differential equation, and in fact this equation has no explicit solution known. I mean, you can kind of write some kind of solution with very complicated function, but that's not the point. The point is it's not the solution is not simple. So, and also it does not respect this this formulation. Here we just add one dot. So to treat this as in the previous model, we introduced the idea to have this geometrical representation, is to introduce this variable y. Here, y will be kind of the velocity of the pendulum, okay? And so if you define that, then y dot is equal to minus sinus, okay? So you can check now that if you replace here y by x dot, you will have x double dot, and so you will get back the exact same equation. So in fact, what you just do is just you replaced one equation with two derivative with two equation with one derivative. Okay, so that's just you do, and by doing that, in fact, it allows you to simply interpret the flows of this equation, the dynamics. So as I say, if x dot is positive, when y is positive, then x will increase. And the same is true for y dot. When minus sinus x is positive, y increase, etc. So you can see, for example, at this point, minus 2, here I plot x, and here y. At when x equals 0 and y minus 2, the how will evolve my flow, it will be in the direction x minus 2 and 0 in the direction y. And similarly here, okay? So you see, kind of see the trajectories here. So in fact, I will show you dynamic solver. So it's developed by Sebastian Moch, okay? And basically it's just solve this equation. And if I start very close to the origin, 0, 0, for example, I see my trajectory now is doing kind of elliptic shape, okay? Then if I start closer, I will do this kind of ellipse. If I start with a larger velocity, in fact, at 0 angle, then I will do this kind of eye pattern, okay? And if I start with very high speed, you see I'm not doing a close orbit. Here it's close orbit. So there is a point here where where the close orbits are not close anymore, okay? So it's about here, okay? Sorry. And when the orbit is not close anymore, it's just the fact that here my initial push to the pendulum was so big that the pendulum is doing a full cycle, okay? And because it's 2 pi periodic, it will eventually go back. But in the simulation, you do not see it because it's not 2 pi periodic. So now, if I want to model the friction, the damped harmonic oscillator, I add this term. So I hope you've seen that. So by just adding this first derivative, my model now has some friction. That models, for example, the contact with air, and that it cannot oscillate forever. Okay, so in this version of the description, so it's still the same now, it just adds this minus gamma y, okay? And you see now my trajectory, if I would plot them, these vectors arrow, okay? Now they all point at the trajectory, all end up here. And in fact, we can see it in the model. Here I add the friction term, so 0.2 of friction, small friction, and you see that instead of doing perfect circle or ellipse, now I have a spiral, and I slowly go towards 0. And in fact, at 0, 0, so it means the pendulum, it has 0 velocity and 0 position, it will stop. So now, I think you're quite convinced. So what does it mean? It means 0, 0 should be a steady state. And we'll check that in a moment. So how to know what is a steady state? You just say it stopped moving in x and y, so it's 0, 0, and I just solve this equation. This equation have 3 solutions: the 0, 0, 1, and the pi plus minus pi in x, and 0 for y. You can check that sinus p or pi or minus pi is 0, indeed. So these are steady states, and now we ask, are they stable or not? To check that, the idea is you decompose x into the steady state plus some perturbation. I call straight x and straight y, and you linearize. So basically, you end up linearizing this sinus x into just x, okay? And you end up with a matrix system. So maybe you are more familiar with this type of matrix forms, and this matrix you can deduce the eigenvalues, and the eigenvalues are simple to get. just this. And once you have that, you know that your solution, you know exactly your linearized solution, it is as this form. So it's a sum of the two eigenvectors and eigenvalues sum up. Okay. So now the stability is just looking at lambda plus or lambda minus and see if the real part is positive or negative or zero. Because if it's positive, the real part, then perturbation will grow in time. And if it's negative, it will decay in time. So it means that your perturbation will decay. So you will go back to the 0, 0 state. So it means here you will see it's stable. So if I start here, I will come back here. Okay. And if it's 0, it means I will neither go far from the equilibrium, neither I will go closer. Okay. So if I just sum up, in the case where there is no friction, okay, as you saw, there was full cycle and I did not approach 0. So that's why the eigenvalues were on the with a real part 0. So if I plot them in the real part of lambda and imaginary part of lambda, they are on the axis. They are purely imaginary. And you can check that by putting that to 0, you indeed have a complex number. Okay. Now, if I have some friction, so gamma is not 0, then I indeed have a real part which is negative, and plus some complex part. Okay, so that's why we have oscillation plus dissipation. So we oscillate and we slowly dump to here. While in the case without dissipation, we just had oscillation without approaching 0, 0. Okay. The two over steady state are always unstable. We never approach them, in fact. So now let's go to another model, dynamical system model, which is called the Locta-Volterra model or prey-predator model. So what does it model? It's a simple model that, see, the equations are not very complicated. Again, finding the exact solution of the system is complicated. So the idea is that X now is the number of prey and Y a number of predator in some, let's say, forest. Okay. And now with the dynamical system analysis, we'll analyze this equation. So here we have the linear terms, here the nonlinear terms. So these terms just mean that if I let alone my prey, my rabbits, let's say, alone, they will grow and increase their population number, okay? Because this is positive. Then, similarly, if I let my predators, the foxes, alone in the forest without prey to eat, they will just die, okay? Because they need prey to sustain. So that's why it's negative here, okay? Now, so this term, it looks like the friction term we had. And in fact, it's similar interpretation. Okay, so now we have also the nonlinear terms, and these nonlinear terms, they models the interaction between the prey and predators. This term means that my prey will be eaten by the predators, and so that's why it's a negative number. By the X will be eaten by the Y basically, and here Y will increase. That's why it's a plus by eating prey. Okay. And the coefficients are just modeling the sensibility of that process of eating, basically. So we can do similarly and look at the dynamical model. So here is you can find that with at this site, okay? And I thank the guy who did that. And so basically by here you can play and tune all the parameters and look at the trajectories in the phase space. So here, for example, if I start at this point with, I have this number of rabbits. Of course, you cannot not have half number of rabbits, but imagine it's possible. And then so I want to interpret the dynamics. Why is it doing this cycle? So if I have a low number of rabbits, um, then the population of foxes diminish, okay, and then because the population of fox diminish, the rabbits can grow again in numbers, and when they grow again in numbers, at some point the fox start to eat them because there is a lot, and then the population of rabbit decrease while the fox increase, and then again it end up here because there is not enough prey, so the fox population is slowly dying, and then it go back again in cycle. So here you can play with this parameter, and for example, if you look at very small gamma, it means that when fox eats rabbit, it doesn't help them to reproduce. Okay, so here it's a very extreme case, but in this case, it just means that the population of foxes will die in time, because when they eat prey, it does not do anything, because I put 0 here. Okay. So you can also look at with this model and put it here, and look that indeed it's doing oscillation. So basically, just what you learn from this model is that the two population will oscillate, and they are kind of related. Okay, so here it's very slow, but basically it means that at this time of the phase space, it's very slow, and then it's getting quicker here, and then there is a slow phase, a fast phase, etc. Okay, and you see the closed orbit forms. So now, how do you theoretically, how do you study that? Again, you study that by looking first at the steady state, and there is two: the one with 0, 0 population, and the one with non-zero and non-zero. Okay, so the 0, 0 state means that everybody is dead and nothing happened. Okay, so it's not very interesting steady state, and it is unstable because one of its eigenvalue is positive. Okay, while the other is negative. Okay, so but the steady state we are interested in is this one. Okay, and you can check that if you plug that in the equation, you have 0 indeed. You have a steady state. So if you do as before and perturbate this steady state around the, you will have with small perturbation and linearize the equation, then you get again this matrix system. And you see it is very similar to the previous one. Okay, if we look at this one, it is 1 here and -1 here, and here imagine is 0 because I have no damping. Okay, and indeed here I have 0, 0 and minus and positive number here. So without any computation, we could guess that already the eigenvalues are imaginary, pure imaginary, so neutral eigenvalue. Okay, so what you learn from that is that two dynamical systems can have a very similar dynamics because they have the same structure. And we did see indeed that there is some oscillation as before, but instead of being around the 0, 0 point, the oscillation are around this point, which is at the center here. Okay, the closer you get here, the more it looks like oscillation here. Okay, so now I jump to another model. Okay, so this model is an economics model, and also sometimes I've seen it's called the class struggle model, and basically it models how the employment rate is related to the wage share of the worker. Basically, U is the share that the workers will get from the work they did, and the rest is obviously going to the boss. Okay, so U is this quantity, V is the employment rate, Okay, and there is in the good win, so he put this equation basically, and U and V are interconnected. So now, if you look closely, you see that this model, in fact, has exactly the same structure, despite having different coefficient. Here is just constant coefficient that you can read the paper I quote to have all the explanations, but it's just constant. But if you look closely, the form of this model is exactly the same as this model, in fact. Okay? So what does it mean? It means that in this model, the worker's income share is the predator, okay, and the employment rate is the prey, okay. So basically, it means that, and here I use this plot that I found in a paper, okay. Here they show the cycle, one cycle as in the prey-predator model. The only difference is they put the predator, which is the wage share, here in the x-axis and the employment rate here. So as before, you can kind of interpret with economic terms this time the different part of the phase space. So here, when the wage start to be too high, uh, and it's here increase and the employment rate also increase. It's the depression part. Then because they keep increasing the employment rate, they have to diminish the wage to the workers, so workers are less paid. Then then here is the what they call boom, is the wage diminish and the employment rate also diminish, which sounds not very good. Then there is the recovery, when the wage start to increase again, but the employment rate still decay. So when you look at just this model, you can have this oscillation. So according to this model, basically the wage and the employment rate cannot stay high both. They have to go in cycle. So that's what is predicted by this model. Of course, it doesn't mean it is the truth. It is just a model. And maybe some features can modify the model, and maybe this model is completely wrong. But at least with it shows that a simple coupling, let's say, between employment rate and wage brings this oscillation. So if in reality you see oscillation of these two quantity, maybe you are less surprised now. So in this paper they explain every constant, etc. So my goal is not to explain the two paper, but just to quote some part of it. So in this model, they also study this wage and employment rate, okay, and they study the eigenvalues, etc. And what is interesting is that they quote for Karl Marx, okay, and they translate some of his idea into mathematical concepts, okay, and then they introduce a new variable which they claim is more gives produce a more realistic model. So basically, what they modify here is this row, instead of being just a constant. So this row basically is the terms that provide an increase in the share of the worker, okay? Because there is a plus, and so they claim that this row, in fact, should depend on some other variable, which is y, and they call the memory variable, and this memory variable, you see, it basically increase. So I'm not detailing everything here, of course, but the just the bare understanding I could extract is that This y will augment if u is large enough from this u star, which might be some satisfying wage share, okay? And if it is above, then y is increased. And then here in this term, now y increase also, okay? So it means that this term is large. So it means that the wage will stay high. So basically, it just models the fact that if employee have a nice wage share, okay, they basically don't want to lose it, and they remember that, and it introduces a new dynamics. So instead of having a two-dimensional system here, we now have a three-dimensional system. So of course, to plot that, it's a bit tricky, but here we can just choose to plot v and u, and y is evolving in the background if you want, and and so they do that, okay. Um, and basically here is the plot where they change the row 2 here, okay, this constant in front of the y, and basically here if it's low, it's you kind of see the oscillation we saw before, but when you increase it too much, you see what it is called a chaotic behavior. So there is a doubling of period. So I'm not defining what is chaos really mean, but basically it means that the system has some trajectory. If you start from two very different initial conditions, here or here, for example, your system might be completely different. And here you see, if you keep increasing row 2, then this is one trajectory. You see it fold and fold over and over. So now the system is exhibiting very complex behavior. Okay, so it's called chaos. And so the point of that, there is two points, is that you can modify your model as you want. Then it might be more realistic. And the second point is, from the mathematical point of view, you have now a three-dimensional system which is very rich in the behavior compared to just the previous one here, where we just have simple oscillation. And the mathematical analysis of that now gets a lot more trickier. You can still find steady state and do the spectral analysis, but it doesn't mean you will capture this kind of crazy oscillation I showed. So now I will jump to the second part where I describe the synchronization phenomena.